In this section, we will investigate the law of sines, which allows us to find all 6 measures of any triangle, provided we are given 3 of the measures and that at least one of those measures is the length of a side. In a previous chapter, we learned about the congruence axioms. Hi, my name is Tom Atwater. Let's start today's lesson by revisiting those axioms. Side, angle, side, SAS. If 2 sides and the included angle of one triangle are equal, respectively, to 2 sides and the included angle of a second triangle, then the triangles are congruent. Angle, side, angle, ASA. If 2 angles and the included side of one triangle are equal, respectively, to 2 angles and the included side of a second triangle, then the triangles are congruent. Side, 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 SSS. If 3 sides of one triangle are equal, respectively, to 3 sides of a second triangle, then the triangles are congruent. Now, whenever these axioms apply to a right triangle, the triangle is unique. A triangle that is not a right triangle is called an oblique triangle. The measures of the 3 sides and the 3 angles of an oblique triangle can be found if at least one side and any 2 other measures are known. There are 4 possible cases. Let's take a look at those 4 cases. Case 1, one side and 2 angles are known. That's side, angle, angle, or angle, side, angle. Case 2, 2 sides and 1 angle not included between the 2 sides are known. For instance, side, side, angle. Now, this case may lead to more than one triangle. Case 3, 2 sides and the angle included between the 2 sides are known. Side, angle, side. In case 4, 3 sides are known. Side, side, side. So, in this section, we will be discussing cases 1 and 2, which require the law of sines. Cases 3 and 4 require the law of cosines, and we will be covering that in the next section. Let's take a look at how the law of sines is derived. In any triangle, ABC, with sides, little a, little b, little c, we know that little a, or side A, over the sine of A is equal to the side B over the sine of B. We also know that side A over sine of A is equal to side C over the sine of C. And we know that side B over the sine of B is equal to side C over the sine of C. Now, this can be written in a compact form where we write little a over sine A is equal to little b over sine B equals little c over sine C. But I want to stay on this because I want to also point out that because we will normally deal with 2 of these ratios at a time, and it's in its proportion form, remember that you could also write this, since it's a proportion, we can also write it where we have the signs on the top and the sides on the bottom. So in other words, I can also rewrite this as the sine of angle A over side A is equal to the sine of angle B over side B. And if I wanted to continue, I could, of course, write that it's equal to the sine of angle C over side C. All right, so knowing that will help us later on because depending on which variable we want to find, it would be good to have that variable already in the numerator. Now, let's take a look at an example where we know the measures of 2 angles and the length of one side. In this example, we have side angle, angle, where we are given the measures of 2 angles and the length of the side opposite one of the angles. So solve the triangle ABC if angle A is 32 degrees, angle B is 81.8 degrees, and side A is 42.9 centimeters. Let's take a look at this picture, which shows us a triangle, ABC, and the given information labeled in the triangle, and then those pieces of information we don't know are labeled with their corresponding letters. To solve this problem, let me redraw this on the board because we're interested in finding all three unknown parts of this triangle. So the triangle is just a general triangle with A, B, and C. And what we know is that angle A is 32 degrees. We know that angle B is 81.8 degrees, and we know that side A is 42.9, and it's centimeters, but I don't necessarily have to write that. Now, in terms of the missing parts, we are missing side B, we are missing side C, and of course, we are missing this angle C. So, what we now want to do is use our law of sines. We want to solve the problem using the law of sines. Well, we have angle A and the side opposite it, so we know that that's one of them. To find the measure of angle C, all we have to remember is that the three angles of a triangle add up to 180 degrees. So, for example, we would say that angle C is equal to 180 minus 32 degrees plus 81.8 degrees. We add these two together, which represents those two, subtract from 180, gives us angle C. So this is going to be angle C is 180 minus the 32 plus this gives us 113.8 degrees. That gives us an answer then for angle C of 66.2 degrees. Okay, so now we have the three angles. We are going to set up and let's find side C first. So for finding side C, I'm going to put the side C on the top, which is what I referred to when I was showing you the law of sines. And then this would be the sine of angle C, 66.2 degrees. And that's going to equal the side A, 42.9, divided by the sine of 32 degrees. So what we now have then is simply this. Little side C, or little c, so that side C, is going to be equal to, we just need to multiply the sine of 66.2 degrees times the right-hand side. So we would have 42.9 times the sine of 66.2 degrees, all divided by the sine of 32 degrees. That will give us the answer C is equal to 74.1 centimeters. So that's our answer for side C. I now need to find side B, and we'll use the law of sines to do that, and I'm going to rewrite that over here as little b over the sine of angle B, which is 81.8 degrees, and that's going to equal little a, which is 42.9 over the sine of angle A, 32 degrees. That means B is going to equal 42.9 times the sine of 81.8, all divided by the sine of 32. And therefore, side B is equal to 80.1 centimeters. So that gives us the three missing parts of that triangle. Let's take a look at another example where we know the measures of two angles and the length of one side. In this example, we have angle, side, angle, where we are given the measures of two angles and the length of the side between the two angles. A surveyor wishes to measure the distance across Big Muddy River. The surveyor determines that angle C is equal to 112.9 degrees, angle A is equal to 31.10 degrees, and little b, that's side B, is equal to 347.6 feet. Find the distance A. And here's the graphic that shows the Big Muddy River and then the information that was given to us that the surveyor has been able to find. So we have to find in this graphic, we're looking to find the distance across the river. And we have the angle A, which is opposite, of course, side A, which we need. Now we have side B, which means we need to know angle B right here. So therefore, the way to find angle B, of course, is that we already know angles A and angles A and C. All we need to do is add them up and subtract from 180. So let me redraw the picture on the board and then calculate what we need to know, because we're going to use the law of sines. We have one side, the angle opposite it, and we have the other side, but we need to find that angle B first. So our picture then is the distance A across the Big Muddy River, and then the rest of the triangle, and we know this is 112.9. We know that this is 31.1, and we know that this is 347.6 feet. So for angle B, let me label that. Angle B, we have that it's going to be 180 minus the 112.9 plus the 31.1. And when we add those together and subtract from 180, we will get 36 degrees for angle B. So I can put my 36 in there, and now I can set up the law of sines to find side A, the distance across the river. So I take A over the sine of angle A, so over the sine of 31.1 degrees. That is going to be equal to side B, which we know is 347.6 over the sine of angle B, which is what we just calculated, 36 degrees. So that means A is equal to 347.6 times the sine of 31.1 divided by the sine of 36. When we calculate all of that out, we will find that it's 305.5 feet across the river. Well, now it's time for you to do a problem. Solve the triangle with angle A equals 37 degrees, angle C equals 95 degrees, and side C equals 18 meters. Pause the video to work on this problem, and when you are finished, restart the video to check your solution. Drawing a sketch of the triangle will be helpful. Welcome back. Let's see how you did. I will start by sketching the triangle. So you'll notice that whenever I sketch a triangle that's just a general one, they all seem to look the same, and I label it A, B, and C. The information we were given is that angle A is 37 degrees, angle C is 95 degrees, and that the side C was 18 meters. we need to solve the rest of this triangle, which means we need to find side A, we need to find side B, and we need to find angle B. Let's start by finding side A. I take side A over the sine of A equals side C over the sine of angle C. So A would be equal to 18 times the sine of 37 over the sine of 95. And when I work all of that out, it works out to 10.87 or so, but let's just round that off to 11 meters. All right, so now, in order for me to find side B, I first have to know what angle B is. But again, we have two of the angles, so all we need to do is add those up and subtract from 180 degrees. So it's going to be minus 95 plus 37. Adding those together, we get 132, which we subtract from 180, and we'll find that angle B is 48 degrees. Now we can set it up to find side B. And we would say little b over the sine of 48 degrees is equal to C, which is 18, over the sine of 95 degrees. Again, I would multiply the sine of 48 degrees over to this side, do my calculation, and I would find that little side B is equal to approximately 13 meters. I hope that's the answer you got when you worked on that problem. All right, now, when we are given the lengths of two sides and the angle opposite one of them, it is possible that we have 0, 1, or 2 such triangles. Let's look at the conditions required for each case. If angle A is acute, we have the following possibilities. It's possible, as you can see, that when the information given, that we end up with the sine of B being larger than 1, and that happens if side A is less than the height of the triangle, which is right along here, which is then less than side B. Now you should remember, of course, that we can't have a sine of an angle greater than 1, and therefore no triangles actually work there. The other way to look at it is that the length of A is too short to create a triangle. Well, in the next case, we're saying that the sine of angle B is equal to 1. And that means that angle B is 90 degrees. And you can see, therefore, we have our right angle, and it's just, therefore, a right triangle. And in this case, we are saying that A is equal to the height, because that's how you create the height, by the perpendicular, and that is less than side B. All right, well, there is another possibility, which is that we have the sine of B is between 0 and 1, which is what we typically would expect. In this case, we're saying that the side A is less than or equal to the length of side B. Is greater than or equal to the length of side B. If that's the case, that the A is greater than or equal to B, we have one possible triangle. Well, what if, again, the sine of the angle is between 0 and 1, which is what we expect. However, this time the length of A is less than the length of B. What happens? Well, you can see from the diagram that we have two possible triangles. I will outline the little triangle, or what I'm calling the little triangle, in this red, where we create that triangle. And that's with this side of A. However, you can see, and I'll outline the next triangle in blue, that we also could create a triangle in which A is over here, and we still have the conditions met that A is less than B, and that the sine of angle B is, of course, between 0 and 1. Now, let's take a look at the possibility when we have an obtuse angle A. So you can see in this that angle A is now obtuse, meaning that it's between 90 degrees and 180 degrees. In this case, we look at and say that the sine of angle B is greater than or equal to 1. And what you'll notice again is that if it's greater than 1, obviously it's not possible. But it's also not possible to be equal to 1 because that means B would have to be a 90-degree angle. And we can't have a 90-degree angle along with an obtuse angle A because then it would be more than 180. Therefore, we do not have any possible triangles. Well, let's take the next case where the sine of B is between 0 and 1, which is what we expect typically, and that side A is in fact greater than side B. If that's the case, then we can form one triangle. And with that one triangle, we can then determine the remaining pieces of information. Next, let's do an example where we solve for triangle ABC if angle B is 55 degrees, 40 minutes, little side B is 8.94, and little a, side A that is 25.1 meters. To solve this problem, let's start off by sketching the triangle. So we have triangle ABC, ABC. We're told that angle B is 55 degrees and 40 minutes. We're told that side B is, actually, what is side B? Yeah, 8.94 meters, and side A is 25.1 meters. I do want to point out that when you look at the numbers that I have in this triangle, it looks a little strange because I have this little side here, and it's 25 meters. I have this longer side, and it's only about 9 meters. Don't worry about redrawing the triangle to make it fit those numbers, because what's important is that I have angle B and side B opposite one another. And of course that I have side A opposite angle A, because everything will come out once we go to do our calculations using the law of sines. So let's do that now. We want to find angle A, so I set up the law of sines. The sine of angle A over the side A, which is 25.1, is going to equal the sine of angle B, 55 degrees 40 minutes, divided by 8.94. So that means the sine of angle A would be equal to 25.1 times the sine of 55 degrees 40 minutes, all divided by 8.94. When I work all of that out on the calculator, I'll get that the sine of angle A is equal to 2.3184 and maybe a few more numbers. Well, wow. You should say to yourself, wait a second, something's not happening there, because the sine of angle A cannot be greater than 1. There can be no such angle A, and therefore, we can't have a triangle with the given information. All right, but now let's look at another example where we can actually get a triangle. Solve triangle ABC if angle A is 55.3 degrees, side A is 22.8, and little b, side B, is 24.9 feet. As always, to solve a triangle like this, we want to sketch it first. So we have triangle ABC. We're told that in this case, angle A is 55.3 degrees. We're told that side A is 22.8 and that side B is 24.9. So we can start by solving for angle B using the law of sines. So we would say the sine of angle B over side B, 24.9, is equal to the sine of angle A, 55.3 degrees, over 22.8. And then to solve that, all we need to do is multiply 24.9 to the right-hand side and find that sine B is equal to 24.9 times the sine of 55.3 over 22.8, and that gives us an answer of sine B equals 0.8978678. Now we use inverse sine on our calculator, and then we find that angle B is equal to 63.9 degrees. So angle B is 63.9 degrees. Now, remember that we said it's possible that we get two triangles from this, and we need to assume that we will, and then check to make sure the answers that we calculate actually create a triangle. In other words, we have a possible angle B sub 2, which is going to be 180 degrees minus 63.9 degrees. And if it's going to work, we'll check the answer for 116.1 degrees. So what we need to do is verify that 116.1 is valid, and we do that by adding 116.1 to the measure of angle A, and that total, that is 116.1 plus 55.3, gives us 171.4, which is less than 180, which means that that triangle is possible. Thus, there are two valid triangles for the given information. Since there are two possibilities for angle B, 63.9 is for first angle B, and B2, the second angle B, is 116.1. That means we have to solve two possible angles C, and therefore two possible sides C, which means you'd have to use the law of sines to find each of those. I'm going to leave that up to you, and repeat using the law of sines to calculate lengths for angle C1 and the lengths for angle C2. Now on to the ambiguous case, which could result in 0, 1, or 2 triangles. Let's look at the guidelines which we use to determine how many triangles there are. Let sides A and B and angle A be given in triangle ABC. The law of sines can be used to calculate the value of sine B. Number one, if the sine of B is greater than 1, then no triangle satisfies the given conditions, because you can't have a sine of an angle greater than 1. If the sine of angle B is equal to 1, then the triangle satisfies the given conditions, and in that case, angle B is equal to 90 degrees. Number 3, if the sine of angle B is between 0 and 1, then either 1 or 2 triangles satisfies the given conditions. In part A, if the sine of B equals a number k, then we have B sub 1 equals the inverse sine of number k, and we use B1 for the angle B in the first triangle. Then we let B sub 2 equal 180 minus B sub 1. Then if A plus B sub 2, that is if we add the given angle plus this newly calculated angle, and that's less than 180 degrees, then we know a second triangle exists, and in this case, we would use B sub 2 for the angle B in the second triangle. So let's look at an example where there is only one possible solution. Solve triangle ABC given that angle A is 43.5 degrees, side A is 10.7 inches, and side C is 7.2 inches. So we'll start off by sketching a triangle. A, B, and C. We're given the information that angle A is 43.5 degrees, and that side A is 10.7, and that side C is 7.2 inches. So we would start this with the information that we're given, obviously, angle A and its side opposite. We have the side opposite C, so we're going to find angle C first. So the sine of angle C over side C, 7.2, is equal to the sine of angle A, 43.5 degrees, over side A, 10.7. So sine of angle C is 7.2 times the sine of 43.5 degrees divided by 10.7. And when we calculate that out, we'll find that sine C is equal to 0.46319,186. In other words, sine C is equal to 0.46319,186. When we use inverse sine in the calculator, we'll find that angle C is equal to 27.6 degrees. All right, well, what about the possibility of a second angle C? The way we calculate it is we take 180 degrees minus the 27.6. When we do that, we get that the second angle, that is C sub 2, would be equal to 152.4 degrees. So another possible triangle may exist. However, we have to check. In other words, we have to take the 142.4, which we're saying is a possible angle for B, and we need to add it to 43.5. However, when we add those together, that sum is 195.9, which means that it exceeds 180 degrees. So that means that this is not a possible answer. There is only one triangle. That is to say that angle C, 27.6 degrees, is the only value for C. So let's write in 27.6 for angle C and realize now that we add these two together, subtract from 180, and that will give us angle B. So 43.5 plus the 27.6 adds up to 71.1, which we subtract from 180 degrees, and that gives us that angle B is 108.9 degrees. So now to find side B, we simply set up a law of sines with sine B, little side B over the sine of angle B, which is 108.9 degrees, is equal to, we'll pick, it doesn't make any difference, side C over the sine of side C, which is, I'm sorry, of the sine of the angle, 27.6. When we go to find B, we just need to multiply the sine 108.9 up to this side. So little b will equal 7.2 times the sine of 108.9 divided by the sine of 27.6. And when we work that out, we'll find that B is approximately 14.7 inches. All right, a lot of great work with the law of sines today. So in this lesson, we learned about how to use the law of sines, which allows us to find all 6 measures of any triangle, provided we're given 3 of the measures and that at least one of those is the length of a side. We found that there may be 0, 1, or 2 valid triangles. Be sure to work the exercises that your teacher assigns, and we'll see you next time.